Okay, so let's talk about scientific notation. Scientific notation is a different way of writing numbers, especially, this is really good, if we have very large numbers or very small numbers. Numbers that would be written like very small decimals or very large numbers, right? Obviously, carrying all of those zeros in these numbers makes it a little bit difficult to have to do some math with. So we use this for convenience. And the way it works is this. In scientific notation, we have something called a coefficient multiplied by some base number raised to the exponent n. That base number is always 10 for us, so that's sort of a fixed one. We just need to be able to determine the exponent and the coefficients. Now, what is a coefficient for us? For the coefficient, whenever we discuss it, the coefficient is going to be a decimal number, usually based on coefficient. There we go, coefficient. There we go. Usually based on this number right here, what it is, it's going to always consist of a number followed by decimal places. And so there's always one figure before the decimal place. Right? So we need to be very careful to rewrite it so that we have that. But what could we do? Well, we might notice a few things. Now, I'll just take a really basic example before I get to these two. Let's say I have 270, the number 270. What do I know about it? Well, 270, right? This is the hundreds place. This is the tens place. This is the ones place. And in this number, we could think of it as being, if we wanted to convert this, right, we could convert this into 27.0 times 10. How do we know times 10? Well, anytime we multiply by 10, we start shifting the decimal to the right over here, right? So 27 times 10 would be 270. But if we want a coefficient, we just want a single number before the decimal point. So what would we have to do? Well, we could multiply this as 2.70 times 100 to get exactly the same value, right? And again, that's just from being able to shift our decimal place to the right, this time twice. Well, 100 is the same thing as 10 to the second power, right? So if we were to rewrite this in any sort of useful way, we might say, well, this is the same thing as saying 2.7 times 10 to the second. And this is the scientific notation for that number, 2.7. Our coefficient is 2.7, right? We just have a number followed by the one decimal place, times 10 to the second power. And all that means is that we shifted our decimal to the right. So we could think about some of these numbers right here. Another way of looking at this is that if I had a number that was smaller than 1, right? Let's think about 0.023, right? We dealt with this, right? Let's say when we wanted to express this as 2.3%, right? What did we do? We shifted the decimal twice over. Well, we can do the same thing, right? If we start multiplying by 10, this would be a little bit like saying 0.23 times 10, right? Or times 1/10, right? Because dividing by 10 always moves the decimal over. But that would be the same thing as saying 2.3 times 1 over 100, which means that we move the decimal over twice, this time to the left, to get back to the original number, right? So if you think about what we've actually got right here, we're just, when we shift these numbers over, we're dividing by 10 to get back to the original number, right? 1 over 100 is the same thing by our decimal rules as 1 over 10 to the second, which is a lot like saying 10 to the negative 2 power. And so really, our coefficient, 2.3, would be multiplied by 10 to the second. Right? So that would be our scientific notation for this one. So if we're converting these over, what we're going to think is this. Anytime we've got a decimal that's smaller than 0, smaller than 1, what we're going to do is that we're going to shift the decimal place to the right until we reach one decimal figure before the decimal point, and that is the power for our tens right here, right? If we're moving to the left, that gives us a negative power like it did right here. So this is really going to be like saying 3.94 times 10 to the negative third power. I had to move my decimal over 3 places right here to make that work. Right? So this is what I would be thinking for as far as my decimal right here. How about this other guy, this big fellow over here, 876,200,000. Well, what do I do with that? That means I have a decimal over here. And this time, kind of like what we're going to do, we're going to get a large decimal right here by shifting that decimal over. We're going to count how many places we need to go over here to the left. 1, 2, 3, 4, 5, 6, 7, 8 places. So if we note the 8 places that we have to shift this decimal over, we could rewrite this as 8.762 times 10 to the 8th power would be the equivalent for this guy. All right. How about going the other direction? What if we want to convert from scientific number to just a numerical form? Well, we're really thinking about this in the same way that we did to the left, except this time we're reversing the steps. We've got 10 to the 9th, right? So if it were like this guy in blue, what we'd be saying is that we're going to have to take 5.81 and move this decimal over 9 places, right? So if we go 9 places, that's 5, let's see, once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times. So if we put the commas here in the right place, looks like we got 5,810,000,000 as the decimal equivalent of our scientific notation 5.81 times 10 to the 9th. How about this guy right here? We got 2.4 times 10 to the negative 7th. Well, in this case, where we had the decimal form and we moved the decimal to the right and got our negative exponent, this time we want to move the decimal to the left. This time 7 places. Right? So that's going to be like 10 to the negative 7th, 1 over 10 to the 7th, whatever that is. But in this case, the way we're going to look at it is that if we start out with the decimal place between the 2 and the 4, we're going to go over 1, 2, 3, 4, 5, 6, 7 total places. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 places, 7 places. So our number right here, our result, 0.00000024 is the decimal equivalent of 2.4 times 10 to the negative 7th, right? So remember the rule right here. We're saying that if we're going from a number to scientific notation form, moving places to the decimal places to the left gives us a positive exponent. Moving decimal places to the right gives us a negative. Reversing that situation, if we've got a positive exponent, we're moving our decimal places to the right to put it in numerical form, taking our 2.4 and we have a negative exponent, moving our decimals to the left to get the decimal form. More in the next video.